Recording in progress.
Great Monday morning. Am I on? I am on. How are y'all doing today on this fine day after Halloween?
Hello. Just getting ready for the week, you know?
Yeah. Well, it's been an eventful week here at my house. My wife's been sick the past couple days. I'm sure she's getting over it, but her voice is still raspy. I actually, I'm doing okay, but it felt like yesterday like I was fighting something off, although I feel pretty good today. My 16-year-old, he's been sick the last week, still sick. Got the strangest thing. He started out with a fever for about 3 days, no other symptoms. And then just in the last 3 or 4 days, he's got the runny nose and the cough going. And then my youngest we also managed to stay healthy. And then just last night, after going trick-or-treating with all his friends, he goes, I feel like I got a sore throat now. Great. So, everyone in the house is sick, except me. So, I don't know what's going on. Well, clearly a cold is going around. Everyone's been tested. No corona, just run-of-the-mill cold. But it's just weird that in some people it's lasting like a whole week of not feeling any better. So that's what I mean by it's been eventful. Everyone's just been feeling miserable. But I guess that's what they said, is like with everyone having been cooped up the last year and a half, suddenly they think colds and the flu are going to run rampant this year because everyone's starting to get back together. Is that better for the music? I may eventually just turn it off.
Yeah, that's good.
It's hard for me to tell because the mix of sound that comes into my headphones is a little different than the mix that you get. Okay. Well, let's see. What did we do last week? Did we do combinations and permutations last week? Or was that the week before? I don't remember. Oh no, probability. That's right, we did probability. So we're down to probability now. And we're moving on to the next stuff, which is an introduction to graph theory. And by graphs, I don't mean the kind of graphs that are typically seen in like an algebra or a geometry class with the x and y axes and the squiggly lines on it. This is a more general notion of what a graph is. And I guess in order to introduce that, I've got like this little game for us to play. And so you might want to get out a piece of paper and quickly kind of like trace or sketch out this picture I'm going to show you. And if I'm not mistaken, I think these pictures are also online. Canvas. Let me go check and see if they are. Zip, zip, zip. Let me look down here. Graphs. No, they're not. So you're just going to sketch these out on a piece of paper, and then I'll give you your instructions. So you've got this that looks kind of like a map, basically. And you can think of each one of these as being like a county or a country or something like that. And the goal is to color in each of the areas. So you might like, color this red and this one over here blue. And if the two regions share a border, like this one and this one, if they share a border right here, then they need to be different colors. But if they don't share a border, like this one and this one, those could be the same color, or they could be different colors. If they come to a corner, like these two right here, like here's a corner right here and here's a corner right here, then that doesn't count. They're not considered to be adjacent to each other. So it's only if they actually share a border like this that they're considered to be adjacent. So you want to use as few colors as possible on this. The question is, how many colors do you need to be able to color in this map? What's the fewest number of colors that you need? So go ahead and give that a shot. Just quickly sketch it out on a piece of paper. It's not really super important exactly the shapes of these borders, as long as you kind of get them arranged in the same way. So what's the fewest number of colors that you need for this? Go ahead and put it in the chat or just say it. Have you got something? Okay, you can, someone on YouTube says 5. You can certainly do it in 5, but can you do it in fewer? Someone else says 3. I think you can do better than that.
Yeah, I think I could do it in 2.
2? Okay. It certainly can't be done in 1. So you say you can do it in 2? Well, so if I colored this one kind of this purple color, then this country over here can't be purple, but I could color it something else, like green. But then this one over here could be purple. It's touching the one that's in green, right? So I can't make it green. It's not touching this one because they come together at a corner. So I could make this one purple as well. And then this one down below is touching the purple one, and it's touching this purple one, but it's not touching this green one over here. So I could color it green. And likewise, this one over the right could be green as well. This one in the middle, that can be purple. And then the two in the corner, those could be purple. And finally, the one at the bottom, that could be green. So I can do this one in two colors. So you kind of get the idea now. Let's do these two. How many colors do you need for this one? And how many colors do you need for this one?
Three for the first one.
You've already got 3 for the first one?
Yeah.
That was fast.
Three for the second one as well.
So we got a guess of 3 for both of those. Can you do better than that?
No.
Well, while we're waiting for other people to chime in with their answer, just go through and make doubly sure that 3 is in fact the minimum number. I can tell you right now that neither of them can be done in 2. The question is, can you do it in 3? Well, let's see about this first one. Now we're eventually going to color them all in, so we just need to start somewhere in the map. Maybe I'll start with this one. I'll make this one purple. And that means that these 3 over here can't be purple. So I'll color this one to the right of it green, and maybe I'll also do this one green. Now here's where we know we're going to need a third color, because this one in the middle is touching the green and the purple, so it can't be either of those colors. Let's make it blue. Okay, so now this one in the corner, that could be purple. And the one below that, that could be green. And the one on the bottom, that could be purple. Oh, but now we got a problem. This one here in the corner is this one, and this one, and this one, and this one. So it can't be any of those 3 colors. It's got to be a 4th color. Or did I maybe do something that could be changed?
Shouldn't you do the last one blue instead of purple?
I could do that last one blue. And then I could do purple. Yeah. So there's a solution that needs only 3 colors. We could do it in 4. But the goal of this is to find the minimum number. So even if we end up finding a solution that needs 4 colors, we could backtrack a little bit, erase some of our choices, recolor them with a different color, and then we can find that we can do it in just 3. Now I think we could definitively know it can't be done in 2 because we have this kind of country here in the middle that's touching, well, it's touching this one and this one, and we know that these two have to be different colors. So this one must be a 3rd color. We almost kind of like picture here that we've got like this triangle going. So anytime you got a triangle, you know that those have to be 3 different colors. We've also got a triangle here, and we got a triangle here, and we got a triangle here, right? So we got all these triangles all over the place. So this one definitely needs 3 colors. Now, the second one. Let's just start out coloring one of them in. So let's give this one a purple color. And then we know that this can be green. This could also be green over here. Here we need blue because it's touching. We got that triangle shape because it's touching this one and this one. And then this one here could also be blue because it's touching this one and this one. This one in the corner is touching the green and the blue, but it's not touching the purple, so we could color that one purple. Now, where should we go next? Maybe here. This one could be green, right? Because it's touching these two. But then we got a problem. This one here in the middle is touching the purple, the blue, and the green. So it's touching 3 of them that must be 3 different colors. I mean, like, well, actually, it's, you know, these two aren't touching each other. So could these two be the same color? Like, could this be purple if we recolored this one over here?
Yeah.
Like, I could make this one purple, but then what color would this one be? I mean, I can't make it green because it's touching this one, and I can't make it blue because it's touching this one. So, if I recolor this one to be purple, then this one can't be, can't remain purple, and it can't be blue, and it can't be green. So it would have to be a 4th color. So it looks like any way I do this, I'm going to have a 4th color. I can now make this one purple. And then finally I could make the top right. I could make that green. So I think I need actually 4 colors to do this one. Now it's possible that I could do it in 3. Maybe I just need to try again. Maybe I just need to erase everything, start over again, and try to draw this one again. See, here's the problem with this. What's this called? This is called the map coloring problem. Cartographers, the people who draw maps, have had this question for hundreds, if not, almost thousands of years. As they're drawing their maps, they wondered, like, what was the minimum number of colors they needed to be able to draw in all the countries. Of course, they could do it in more colors, and makes it a more colorful map. But what was actually the minimum color they needed? Minimum number of colors they needed, and it was kind of long suspected that the answer was 4, but they didn't know why. Perhaps you could draw some maps in fewer than 4, but it seemed like 4 was the absolute minimum in general. Well, actually, I should say it's the maximum. What's the maximum number of colors that you need to draw a map color? I should flip that all around. What's the maximum number of colors you need? And it seemed like the answer was 4. That you could always, no matter how you drew your map, you could always do it in 4 or fewer colors. So there's kind of two questions here is can a map be drawn in fewer colors than 4? And if so, how do you do it? So there's two questions. One is kind of a yes-no question. Can it be done in fewer than 4? And the other is, how do you actually do it? And see, the problem with a problem like this, and this is what is generally known as a problem. It's a thing you need to solve, for which there's no well, let me back up here. Mathematically speaking, a question is something that has just a single answer. Like, what is 2 plus 2? That's a question. It has only one single answer. The answer is 4, and it's always going to be 4. It's never not going to be 4. And so if you're posed the same question again, you can definitively say what the answer is. But a problem is a more general type of a question. It says what is x plus y? That's a problem because you could swap in different values of x and y. And so this is a problem because we could just replace different kinds of different maps. And we ask, what's the maximum number of colors you need? Or what's the minimum number of colors you need? And how would you actually color it in? And the problem with these types of problems, let me get back to that, is that it's very difficult to solve this problem without just exhaustively trying all the possibilities. If I want to know what's the minimum number of colors I need to draw this map in, there's no way to actually just look at the map and go, oh, I know the answer, it's 3, or it's 4. I mean, I know 4 is the maximum, right? But I don't know whether it can be done in 2 or 3 without resorting to kind of a brute force approach. Just try all the possibilities until I stumble across the answer. And even then, I might not know that's the answer unless I exhausted all the other possibilities. So this map we just did, is 4 the minimum number, or do we just need to keep coloring it in over and over again until we stumble across a better solution? So it turns out the map coloring problem is just one of many types of problems in mathematics and computer science for which there's no known quick solution to solving it. You just have to kind of brute force it and try all the possibilities. So this is called an intractable problem. Intractable doesn't mean impossible. Intractable just means it'll take a long time to solve this problem. Long time meaning probably brute force. There's a whole bunch of intractable problems in computer science. One of them we've actually learned about already, and that is the problem of factoring a large number into its prime factors. This is what's needed to be able to crack things like cryptography. The fact that it takes a long time to be able to do that, just try all the possibilities, is what gives cryptography its strength. So the map coloring problem is also one of those intractable problems. We don't know, we meaning computer scientists and mathematicians, don't know a better way to solve this than just simply trying all the possibilities. So this particular problem, the map coloring problem, is interesting in computer science because it was the first one to be proven by computer. I think it was back in the 1970s. Before then, all of these types of problems were proven by hand. Like, someone would actually write out a proof by hand. Here's the reason why this particular problem is intractable. But the map coloring problem was the first one to be proven by computer. And generally, what the researchers did was they first showed that no matter how complex a map is, it can be subdivided into a finite number of smaller maps. And by finite number, meaning like I could break it down into a map that has, like, let's say, only 6 countries in it. And then I can just rearrange all the ways to write out those 6 countries, all the ways to kind of like line them up so they have different borders. I don't know what the exact number was, right? But it's like around 6 or 7, some small number. And then they also showed that every map, no matter how complicated the map is just taking one of those smaller maps and then connecting them together. So once they were able to show that, then all they had to do was just show that it was impossible to color in those smaller maps with what am I trying to say? To brute force them, right? The only way to find out the minimum number of colors was basically to brute force all these and work through all those combinations and show that the number of colors you needed was 4. Okay, some could be doing fewer, but 4 was the maximum colors you needed. It took a long time back in the 1970s for mathematicians to accept that a computer could prove something. And this was basically not a proof by like writing out a sequence of logical steps. This was a proof by showing here's the millions of ways that you could color in this map. 4 is the maximum number that you need. So it just did a proof by exhaustion, a proof by going through every single possibility. I remember seeing like pictures of all the maps, just page after page after page of all these little submaps all colored in. Since then, proof by computer is now a fairly common thing to do. But this was a groundbreaking one because back in the 70s, it was the first one to be shown true by proof by computer. So the number of colors we need to do that bottom one is, I believe it's 4. I've not found any solution that we needed less than 4. Hang on just a sec. Let me catch up on my notes here. So we've solved these problems by coloring in the regions. This ties in with graphs because you could take each one of these maps and you could turn it into a graph. So a graph, at its most basic form, is just a set of vertices, which we'll represent with circles, and edges, which are used to connect the vertices together. And it's very easy to turn one of these maps into a graph. All you have to do is put a vertex inside of each one of these regions. And then everywhere that there is a shared border, you just connect them by an edge. So these two regions share this border, so we're going to connect them with an edge. So it's kind of easy to do that. Everywhere where you see a border, you just draw a line through it and then connect up the vertices. I think I got them. Hope I didn't miss any. So the circle is called a vertex. Sometimes you also hear it called a node. And then the line is called an edge. And now you can solve the same problem, the same map coloring problem, by using a graph instead of the map. Let's ignore the map, ignore that it's back there, and let's just look at the graph. So now what the goal is to color in each one of the vertices such that its neighbors, and a neighbor of a vertex is one that has an edge connecting it. So these two vertices here are the neighbors of the one I just colored in. The neighbors can't be the same color. So this has an edge and this has an edge. So these two can't be the same color as this one. And since these are also neighbors of each other, they can't be the same colors as each other. Here in fact is that triangle that I had talked about. So I'll color this one blue and this one purple. Now here's another triangle right here. So these three are going to have to be different colors. But this one could be the same color as the green one because they're not neighbors of each other. So perhaps I'll color that one green. And then this one here can be blue. And here's another triangle right here. So I know that this third one has to be purple. And again, here's another triangle. So this one has to be green. Here's another triangle right here. So I could color this one purple. However, it's also touching this one. So it can't, this one here, because it's touching the green and the blue and the purple, must be a different color. Okay, I can make this one green. I can make this one purple, or I can make it blue. And there's our same graph, but with 4 colors. So if you want to show that a given graph needs, well, let me back up here. How could you show that you can't construct a graph that requires 5 colors? And for one thing here, we have to put in this constraint to say the graph has to be what's called planar. A planar graph, which means it's drawn on a flat piece of paper. So no overlapping edges, no overlapping vertices. You're not going in the third dimension. You're not doing like bridges and tunnels. Everything has to be on a plane. Usually when I'm doing this exercise in the classroom, some people finish up first, and so I give them the challenge, draw me a graph that requires 5 colors. They work on it for about half an hour or so. If I gave you this graph right here, you can obviously do that in 1 color. And if I gave you this graph, you can do it in 2 colors, right? You need 2 for that. If I give you one that forms a triangle, of course, you'll need 3. Now, here's a graph with 4 vertices. How can I construct the edges so that those must be drawn with different colors? And so to force them to be drawn with different colors, I have to make all the vertices neighbors of each other. I can take this one on the top left, and I can make it neighbors of the other 3. So now that one has to be a different color than the others. But these, however, could all be the same color. So now I need to make them major neighbors of each other as well. So if I take the one in the top right, I can make it neighbors of the one below it. It's already neighbors to the one to the left of it. I just now need to make it neighbors with the one on the bottom left, and I can do that by just going around the edge. Okay, and then this one here, it's already neighbors with this one. It's neighbors with this one. I just need to connect it with that one there. Okay, and then finally this vertex here, it's already neighbors with this one. It's already neighbors with this one. And it's already neighbors with this one. So now this one's going to need 4 colors. Now I've got 5 vertices. I want to force them to all be different colors. So I'll make this one neighbors of the other 4. No problem. And then this one here, I'll make it neighbors with the other 4. I'll go here. I'll go around this way to touch that one. I'll go around this way to touch that one. And then this one here, I need to make it, it's already neighbors with that one. It's already neighbors with that one. I need to make it neighbors with this one. That's easy. And now I need to make it neighbors with this one. But I can't cross over any of the existing edges. So I got a problem. Like, how can I get to this one here when it is completely enclosed by a set of edges? So I'm stuck. I can't like make this one touch this one. There's no way for me to like go around anywhere to get to this one without going over an existing edge. And that makes it a non-planar graph. I got one more edge I could put in right there. But still, I got the same problem. So this is like an informal way to show that there's no way to draw a graph that requires 5. This is by no means a complete proof because all we did was we just drew one graph for which we needed 5. Maybe it's a case of we just didn't arrange the vertices correctly, or maybe we didn't connect up the edges correctly. So what we would need to do is work through all the other possibilities, there aren't that many more, and show that every single one of them is going to run into the situation where we can't complete the graph. That would be a proof. And we'd have to show these are all the possibilities. So not only would we have to run through all the possibilities, we would have to show that these are in fact all the possibilities. Once we did that, we would then exhaustively show there's no way to construct a graph that requires 5. All right, let's do the same thing again. We just put vertices here in each one of the regions, and then we connect them up with edges. And then we start coloring them in. Maybe I'll make this center one purple, and then I can just go around the edge here, alternating between blue and green. Oh, I remember there was something we could do here that was different. Oh, that's right. This one here could be purple because it's not touching the purple one. And this one is green, and this one is blue, and then this one is green. So it turns out that a lot of computational problems, a lot of problems in computer science, can be solved by just turning it into a graph and then solving that problem. Problems like navigation lend themselves very nicely to graphs. I mean, you basically start with a graph, right? You've got to start with a map of a city, and you want to know how to get from where you are to some destination. You're solving a graph problem. What's the shortest route between 2 vertices on a graph? Resource allocation and optimization. I've got a set of resources that are available. I've got a set of entities that want to use those resources. How do I allocate those resources to those consumers of the resources in the most efficient way possible so that consumers aren't sitting around waiting for resources to become available. Resources are being used to the maximum extent. And then there's things like planning problems. There's a famous one called the traveling salesman. Maybe you can think of the traveling political candidate or CEO. Right? The idea here is this person wants to go and visit a whole bunch of, let's say, cities. What is the shortest route through all those cities and come back to your starting point? Or what's the cheapest route if you're maybe flying from city to city and you want the cheapest airfare total? So for a small map, one with only 5, 6, 7 destinations, this is easy to solve. You can actually solve it using brute force. You start at city A, and let's say there's 7 possible cities to go to, so you got 7 possible first destinations, and then there's 6 possible second destinations, and there's 5 possible fourth destinations. So you basically got about like 7 factorial routes to try. Or maybe it's 6 factorial, something like that, somewhere in that order. And that's not too bad. That's like 120 things to try. Your computer can whip through those in a fraction of a second. But let's say you wanted to visit 50 destinations, like the United States. You want to visit each one of the states, each one of the capitals of the United States. Well, now you got 50 factorial possible routes to try. 50 factorial is a huge number. I mean, if your computer can evaluate, let's say, 100 routes per second, it's still going to take years and years and years for it to calculate this route. This is called an intractable problem. Can't be done quickly. Actually, this is one of the problems where we don't know a good way to solve this problem quickly. So, turns out that if you can take a problem and turn it into a graph problem, sometimes there's an easy way to solve it. Not all graph problems are intractable. I just want to put that up front. A lot of them have quick, easy solutions. You've seen navigation problems that can be done quickly. You just plug in your starting point and your ending point into like Google Maps, and in less than a second, it has calculated a route for you. And the map that Google is using is huge, right? It's the entire world. They can calculate that in a fraction of a second. So there are some problems, graph problems, have very quick answers. Some don't. So let's just go over the terminology again. A vertex is drawn just as a circle. An edge is drawn as a line. There's different kinds of edges. There are directed edges that have an arrow, so you can kind of like go only one way. As you're traversing the graph, you have to follow the edges in the direction of the arrow. You can have weighted edges, so every edge is associated with a number or a value of some sort. This could be things like, it could be the cost of traversing that edge. It could be a physical cost, like dollars. It could be kind of a virtual cost, like the speed at which you're able to travel it, or it could be the amount of resources that you consume in order to travel it, like fuel used. So you got weighted edges. You can also have weighted directed edges. If you have a graph like this, or like this, these are called connected graphs. So every vertex is like connected in with every other vertex. There's no vertices like standing on their own. There's no parts of the graph that are isolated. Kind of a more formal way of saying it is, there is some path to get from every vertex to every other vertex. This one down below would be called fully connected. Every vertex is neighbors with every other vertex. And the one down below would be called disconnected. Some vertices can't be reached from other vertices. Oh, my goodness, I'm sorry. You're not seeing the screen. Oh, that's embarrassing. All right, so you got, let me go over that again. So you got vertex, you got edge, you got directed edges, you got weighted edges. Okay, you already heard those descriptions. You've got connected graphs, in which every vertex is reachable from every other vertex. And whoops, now I got a blank screen. That was even more embarrassing. Now I got to do it all over again. Oh my goodness. Vertex, edge, directed edge, weighted edges, all right, connected graphs, fully connected graphs, and then disconnected graphs. And then this one here is called a tree. Trees are like really a big part of computer science. Trees have things like a root. Trees are always drawn upside down, so the root's on the top, and leaves are at the bottom. And typically inside of, when you're talking about trees, the vertices of the tree are called nodes rather than vertices. Okay, sorry about not being able to see my screen. Hopefully you got caught up now. So I want to emphasize that when you're talking about graphs, the actual shape of the graph doesn't matter. It's how they're connected. So if I have a graph like this, sorry about the squiggle line. You know, lines can be squiggly or straight, you know, so that's the same graph. That's also the same graph. Just the vertices have been rearranged, but they're all connected up in the same way. So we might say these are topologically equivalent to each other, even though they look different. Okay? So when I draw a graph, the fact that it's not like shape-wise exactly the same, but if they're, it doesn't matter as much as how they're connected. Are the same vertices connected by edges? Then it's an equivalent graph. So any questions about all that terminology stuff? So next time on Wednesday, we'll talk more about algorithms that you can do with graphs. Like how can you do the shortest paths problem? How can you do a problem for resource allocation? Not resource allocation, but different ways to connect up graphs. All right, so one of them is a navigation problem. How do I get from point A to point B as quickly as possible? We'll do that one. Another one that's also useful is called spanning tree. And that is, given a graph, is there a way to connect up all the vertices without necessarily using all the edges? So in other words, taking a graph and removing all the cycles from it. A cycle is when you have a series of vertices that like form a circle, like they're connected up so that you can cycle around those vertices. If you can remove all the cycles, then you basically get yourself a tree. But you want a tree that maybe has the fewest number of edges or something like that. And that could have a usefulness in things like resource allocation. Like you've got all these pipes that need to connect up different parts of, let's say, a landscaping project, or that you need to connect up homes, to deliver water or sewer to the homes. How can you connect up all those homes using as little pipe as possible? You just want to make sure all the homes are connected in, right? But it doesn't matter how they're connected, as long as you're using as little pipe as possible. So we'll talk about those on Wednesday. What I want to kind of show you for the rest of today, we got about half an hour left, is to show you how trees get used in computer science. One application of trees in computer science. So let's say you've got this expression. Maybe it's part of a larger computer program, or maybe you've typed this into a calculator, and I'm going to show you kind of like what the computer does to evaluate this expression or to figure out what its value is. And what it does is it turns it into a tree. At the very top of the tree is going to be the operation you do last, and at the bottom of the tree are going to be all the individual values. In this case, A and 2 and B and 6. So we're going to start with those values, and then we're going to work our way up. So if I look at this expression and I apply the usual order of operations, if I look at this, I know that what I have to do is I have to multiply A and 2 together, and then B and 6 together, then add those, and then subtract 6. Right? That's the order of operations. Sorry, I don't have anything to drink here, and my throat's kind of going a little bit. Okay, so let's write this out. We've got A and 2. And then we're going to multiply those together by forming a little tiny tree out of them. Then we got B and 6, and we're going to multiply those together. Then we're going to add the results of those two multiplications. And then finally, we're going to subtract x. So when the compiler or the calculator sees this expression it needs to evaluate, it turns it into a tree, where the top of the tree is the last operation it does, and the bottom of the tree are the first operations it does. And then it just evaluates this tree from the bottom up. In order to turn this tree into a series of calculations it's going to do, it performs what's called a post-order traversal on the tree. A traversal means to walk from like beginning to end. If you want to traverse, the city park, right? You're going to walk through all the paths of the city park. If you're going to traverse a tree, you're going to walk through the tree, following the edges, going to each one of the nodes in a systematic way. Now we'll get into exactly how to do these traversals next time, but a post-order traversal would go like this. We're going to start here at A, then we're going to do 2, and then we're going to work our way up to the times. So let me write those out. We've got A, and then 2, and then times. And And then we'll come over here and we'll do B and 6 and then times on those. My dog's going crazy. Okay, and then we're going to do plus, then X, and then minus. Okay, so that's a post-order traversal. It's done by going like down here and then, whoops, it's done by going like here to here to here, and then here to here to here, and then here, and then here, and then here. So the cool thing about a post-order traversal is that this is almost exactly the order in which you would break down the problem into a series of more fundamental operations. Like on a computer, if you've taken an assembly language class, you know that the operations on the computer are like load and store, or sometimes just called move. So you want to load something into a register, out of memory into a register on the computer. You've got store, which is to take the answer out of a register and move it back into memory. And then you've got the fundamental operations like add, subtract, multiply, divide, compare, jump. Well, that's basically it, right? You got, fundamental math operations, and then you've got comparison operations. You've got the bitwise operations like and, or, not, exclusive or, and then just branching instructions. So that's basically it. So on a modern processor, you would take, like, let's say, the value of A, whatever memory location that corresponded to, and load that into a register. Call it register 1. And then you take the number 2 and load it in register 2. Notice I'm just following these instructions going from left to right. Then I'm going to multiply register 1 and register 2 and put the answer into register 3. Then I'm going to load the value of B and put it in register 4. Load the value of 6, put it in register 5. Multiply registers 4 and registers 5 together and put the answer into register 6. Then I'm going to add register 3, which is the result of this calculation, and register 6, which is the result of this calculation, and store that into, let's say, register 7. Load the value of X, put into register 8, and then subtract register 7, register 8, and put that into register 9. And then finally store register 9 into wherever the answer goes. Okay, so you take the expression, which is written in what we humans call postfix, but not postfix, infix notation, in which the operators go in between the values that they're operating on. You turn that into a tree. You perform a post-order traversal on this tree, and then you just walk across that list of values from left to right, emitting these fundamental operations, and you've got yourself an assembly language program. It's really what the compiler does. So the compiler takes your expression, turns it into a tree, does a post-order traversal of the tree, and then just turns that into assembly language instructions. And you've got yourself a working assembly language program. It's not optimized. It's not like maybe the shortest way to do it, but it's a good start. And it works. When you take a compiler construction course, you'll probably do this. You'll write a program that takes a mathematical expression with, the 4 or 5 fundamental operators. You'll turn it into a tree. You'll walk the tree doing a post-order traversal, and for every single one of those nodes that you encounter, you'll emit an assembly language instruction. and you'll get a working program out of it. That's how a compiler works. And all I did it for a small expression. A compiler really will take a large program and turn it into a giant tree. All the way starting with the very first thing in your program, public static void, right? All those words become nodes in a tree. And then it just walks the tree from left to right, bottom to top. And it turns that into an assembly language program. Once you got an assembly language, it's very easy to convert it into the native machine code for that processor. You've probably already seen there's some optimizations we could do, like, once we're done with register 1 here, once it's been involved with multiplication, we don't need it anymore. We could recycle it and use it for something else. So we could actually do this whole thing in fewer registers. And that gets into a different problem, a register allocation problem. How can we do this calculation with as few registers as possible? Right now, what I've done here is I've basically assumed that there's an infinite number of registers and just assigned every single variable and every single result of a calculation to a new register. And that's great. And then you can make a second pass through the program and then reassign the registers so you recycle the ones that are no longer being used. So here's how the register allocation problem gets done. And this is also done in your compiler. Let's say this is the program we're executing. A equals C plus D, B equals A plus E, F equals E minus 1. So initially, I might just allocate every single variable to a separate register. Just assume there's an infinite number of them, or there's a number of registers that's equal to the number of variables we have. So I need 6 registers to store these 6 values. I might even, if I want, put the number 1 into an additional register. So here's the corresponding assembly language instructions, just using the variables. So we're going to add C and D together and put the result into A, which is this instruction right here. Then we're going to add A and E together and put the result into B, which is this one here. And then we're going to subtract E and 1 and put the result into F, which is this statement. If we then swap in the variables that we're using, it becomes these instructions. So all I did was I replaced all these variables with these registers. So what we can do here is draw a graph. So what I'm going to do is I'm going to draw a graph showing the interdependencies between the variables. So like right here, I've got A equals C plus D. All 3 of those registers, or all 3 of those variables, are involved in the same statement, so none of those 3 variables could be stored in the same registers. So I'm going to draw that as a graph with 3 vertices, A, C, and D. And I'm going to draw edges between them to show that they're all dependent on each other. And then I have this next one over here, B equals A plus E. So here's B and here's E. And there's a dependency between those 3 registers, or those 3 variables. And then finally, F equals E minus 1. So there's now a dependency between E and F here. And now what I want to do is color in this graph using as few number of colors as possible. This should sound familiar to you. This is the graph coloring problem, the map coloring problem. color in this graph using as few colors as possible. Okay, we'll make this one purple, this one green, and this one blue. And then over here, these can't be purple, but they could be blue or green. So I'll make this one blue, perhaps, and this one green. And then finally over here, this one here can't be blue or green, but I could make it purple. And so I've managed to color in this graph using just 3 colors. I've got purple, green, and blue. And then let me just say that, maybe purple is going to be register 1, green is going to be register 2, and blue is going to be register 3. Purple register 1, green register 2, blue register 3. So now I have a set of new allocations. I still have A, B, C, D, E, and F. Okay, so I'll say A is going to be register 1, right, because it's purple. C is going to be register 2. And D is going to be register 3. B is going to be, it's blue, so that's register 3. E is green, so that'll be register 2, and F will be register 1. And so now my assembly language program, I just swap in the new registers. So I look over here at my original program, I use these new allocations, and now I've got add, let's see, C is register 2, D is register 3, and A is register 1. And then I have another add. I'm looking over here, right? And then I'm swapping in these. So I got A is register 1, E is register 2, and B is register 3. And then finally subtract register 2, the value 1, and then put it into register 1. So I can now do the same calculations using just 3 registers instead of the original, 6.
Does this mean that we can do any calculation with only 4 registers?
No, because you might have interdependencies that result in a non-planar graph.
Okay, thank you.
So you might have really complicated expressions that result in a non-planar graph, and so you might need more than 4 then. But the upshot, I guess, of this is that since you can turn any expression or any program into this graph, and then you want to color in the graph, it means that ultimately the register allocation problem is an intractable problem. For a arbitrarily complex program, you cannot very quickly find an optimal solution for the number of registers needed. You can't totally minimize that to the absolute minimum in a quick way. So most compilers will just come up with a solution that's good enough. Maybe it turns out the optimal solution is it needs 10 registers total, but you could quickly find a solution that requires 12. Good enough. That's okay. Our computer has 30 registers, so we got plenty, right? So it's not so important for a compiler to find the optimal solution. Good enough is usually good enough. And with these intractable problems, finding the optimal solution is what takes the longest. finding a good enough solution can usually be done fairly quickly. Intractable problems, by the way, there's a class of intractable problems for which the register coloring and the map coloring problem is one of them, in which it's difficult to find the solution, but it's easy to check that the solution is valid. Okay, so if you're coloring in a map, it's easy to find, it's hard to find the optimal solution. But once you do find the solution, it's easy to check that it is a correct solution, right? Not that it's the correct solution, but it's a correct solution. If you're factoring a number into its prime factors, it's hard to find the prime factors. But it's easy to check that when you multiply them all together, you get the original number back. When you're trying to crack a hash, trying to crack a password, it's hard to crack the password, right? You got to try all the possibilities. But it's easy to check that the solution you found is in fact a correct one. So with this register coloring problem, it's hard to find the most optimal solution, but it's easy to check that it is a correct solution. It's also relatively easy to find a non-optimal solution, and it's easy to check to verify that it is a correct solution. So, like I said, with these intractable problems, usually finding a non-optimal solution is fairly easy. So, same thing with this, right? You just come up with a coloring that's good enough. You might need more than necessary, but you usually have plenty of registers to work with. Okay, that was actually all I had for you today. It was just this brief introduction to graphs, the terminology of graphs, and then a brief introduction to trees. Hey! You want to say hi to my class? You going to stand on the chair over here? Hi. You're not feeling well today, right? You're not feeling well today, right? Got a sore throat? Yeah?
I'm a bear.
You're a bear? A sad bear. All right, I'll be done pretty shortly.
Okay, books.
Yeah. Okay. All right, so like I said, that's pretty much all I had for you. A brief introduction to the terminology of graphs, what they are, and then showing you a little bit about how graphs, in particular trees, can be used to solve problems in computer science. And you'll discover as you take more courses in algorithms, data structures, and then artificial intelligence, compiler construction, pretty much all of your courses that kind of follow the basic core courses use graphs in some way to solve problems. So being able to turn a problem that looks like a kind of a mathy, wordy problem with a lot of numbers into a graph problem can often lead you to a solution very quickly, because you can find a book on algorithms. And do I have one sitting back here? Oh, you know what? A couple of weeks ago, people wanted to know more about the books I have back here. So maybe I could do that now here. What I tried to do, and this is a whole background that I set up just for like online teaching, is the idea is this is a kind of like a snapshot of my life, if you will, and my interests. So I don't know, can you see back over? Oh, right in the corner, let me move out of the frame so it focuses that. There we go. So I've got like a shortwave radio back there. This is a jar of sand that represents my family. So each one of the colors is one person in our family, and we kind of blended us together to show that we're a family. There are some old calculation tools. I got a slide rule, an abacus, and then this old calculator, sign calculator. Up here I've got one of the very first laptops. This is a Tandy Model 102 computer. It runs for about 2 or 3 weeks on just a set of 4 AA batteries. Very, very neat little computer from the 1980s. I got that. I bought that for about 50 bucks from someone who said it doesn't work, doesn't turn on, and I was able to get that to work. I had to replace a few parts in it, got it to work. And then I got a microscope that I use for like little science experiments, also for working on circuit boards. And then what do I got as far as equipment goes? Over here, this is an oscilloscope, a digital oscilloscope, a Lego robot, and then right here, this is a thermometer actually that's got floating bulbs in it, and they float up and down depending on the temperature. And then finally over here, just off camera, are some old hard drives and vacuum tubes that I've opened up so you can see the platters inside of them. And then finally, this is an old reel-to-reel tape deck right here. So as far as, oh, have I ever shown you this calculator over here? Not the slide rule, this one right here.
No.
I haven't shown you that one. This is kind of a neat calculator. This is one you might have gotten back in the 1960s and 1970s before there were modern digital calculators. This is an analog equivalent of a digital calculator. So first of all, it's got this thing on the top here. This is used for resetting it back to all zeros. You can see you've got all zeros here. And you've got these sliders. You use a stylus, a metal stylus, to move these sliders up and down. And so let's do a simple addition problem. Let's do like, I don't know, 56 plus 72, something like that. So I'm going to put in 56, so I put in my stylus right next to the 5, and then I pull it down, and then that puts the, is it focusing? Focus, come on. There we go, should put a 5 right there in that second position. And then I'm going to put a 6 here, slide it down. And so I've got the numbers now, 56 here. And what I said, I was going to do 72. So I'm going to put my stylus on the 2, and you can see that some of these numbers are now red and some of them are still white. So if I put the stylus in there where it is white, I'm going to pull it down. And if I put it in there where it's red, I'm going to push it up. So I'm going to start from the right as usual, and I'm going to put in a 2 here. And since it's white, I'm going to slide it down. And hopefully if it focuses, you can see this now says 8. And then for the 7, that's going to go in where it's red. So I'm going to push it up, and then I slide it over and come down. There's a little hook on there. And now this reads 2 in the second position. And by sliding it up and over, I've clicked over the next position to a 1. So I now have 128. So when you go up and over, it causes the next, it's kind of like doing a carry, right? It causes the digits here to add up correctly, and then you slide it over and you go click, and it causes the next position to go up by 1. So you're doing your carry. When you do long addition, right, you do that little carry at the top. So let's take 128 and maybe we'll add, I don't know, we'll add 72 again. Okay, so I'm going to start from the right. I'm going to put a stylus into 2. I see it's red, so I'm going to go up and over. And now that has changed this to 0, and it's clicked over this one to a 3. And then I'm going to put in a 7. So 7 in the next column. I can see it's red, so I'm going to go up and over. And it has put in a 0 here, and it's clicked over this one to the next position. And now this says 200, which is 128 plus 72. And so you do this side for addition. And if you want to do subtraction, you do this side. All you do is you flip it over. So now everything that you would have pulled down, you're now pulling up, essentially, and it's subtracting, and it works the same way. All right, so this can do addition, and it can do subtraction. And then if you want to reset it all back to 0, you just pull this up, and it goes back to 0. So this was an old style digital calculator before there were electronics. Digital meaning, you know, it works with individual digits. I really like this calculator because it really kind of like, it actually does the pen and paper type of addition with the carry and everything, but mechanically. It's very cool. So as far as like books over here, this great book here, Foundations of Computer Science. This is available free. This is now like, the authors of this have put it in the public domain. So you can now just download this book for free. Just search for Foundations of Computer Science. And it's got a lot of great stuff in it about like fundamental algorithms. It really does actually start you almost out with graphs. How to measure the running time of algorithms. Like I said, data structures, probability is in here. This is almost kind of like a course in discrete structures. Here, more graphs. Set theory, which we did a week or two ago. Tree traversal, here's depth first search. And then finite state machines, which we're going to be getting to in the next couple weeks. So a lot of the topics we cover in this class are in this book, available for free now. What do we got here? This is an old book called Programming Pearls by John Bentley. I learned about this book in the 90s. And so some of the information here is a little bit dated, although it's been updated for the 21st century. But there are like little hints and tips about how to optimize your programs and how to write programs without knowing the algorithm at first. So there's a whole chapter in here on writing binary search, but writing it in a way that proves that the algorithm, that your program works correctly. Trees, searching trees, compressing space in your data structures so they don't take up so much room in memory. I don't know, I was like a junior or senior in college when I stumbled across this book, and it was just like eye-opening about like, I learned all the fundamental stuff in my classes, and then this like took it to the next level. I was just like, I read this thing cover to cover in a couple of days. I was like, wow, this is awesome stuff. So that's that book. And then I have a follow-up here called More Programming Pearls. There were some interesting things in here about like, sometimes, I'm summarizing one of the chapters, but they said like sometimes it's hard to write a program to solve a problem, but it might be easier to write a program that writes the program that solves the problem. Like, that's called metaprogramming. When you write a program that writes programs. And so you think like, what the heck is that? Like, you know, why would I want to write a program that writes programs? Well, they said like, well, maybe your program here, your problem you want to solve is you want to draw these pictures. Can you see this here? You want to draw kind of like these flow diagrams. And so you want to write a program that draws these things. Well, instead of writing, you know, a program that draws an ellipse, and then a program that, or a subroutine that draws an ellipse, and a subroutine draws arrows, and a subroutine that draws rectangles, and then puts text inside of them. Instead of doing that, why don't you design a language that describes these images? So I have like ellipse that points to a rectangle that points to an ellipse, and then write a program that basically takes a program about the description of this and turns it into the picture. So you're basically writing a compiler, which is really what a compiler is. It's a program that writes programs. I got a book here called Starting Forth. Forth is a very small little programming language that is popular on small embedded processors, and it's a programming language where you can basically program the compiler and the editor and an operating system in a very, very small amount of memory, like just a few kilobytes. But this is a great book on learning the fourth programming language, which beginners can pick up fairly easily. I kind of had a fascination with fourth and fourth-like languages many years ago. What else here? One of the classic compiler construction courses, textbooks. Compilers, Principles, Techniques, and Tools. This one, you hear it called the Dragon book because of the dragon on the cover. I would say, I mean, this is what I learned compiler construction first, so it kind of has a bit of nostalgia for me. But I would say there are better, more modern books than this. Take a compiler construction course. They might use this book, or they might use kind of a more contemporary one. This was state-of-the-art compiler construction back in the 80s. It's moved on from there. This is the Journal of Irreproducible Results. This is a scientific journal, but but it's a satirical one. What they do is these are papers written by serious scientists, but about complete nonsense topics. And they get published in this Journal of Irreproducible Results. Let's see. There's some funny ones in here. This is what here's called cat cars, a newly discovered phenomenon. I guess what these scientists were doing, I guess, tongue-in-cheek, was they were researching cats and their propensity to sleep under cars. And so here's a picture of a black cat sleeping under a car at night. And then, oh, what else is in here? Looking for ones that I can summarize in just a few seconds. Study of nature. Oh, some of these you just have to read them, and then they're hilarious. A new unit of length. The beard second. How long it takes a beard, how far a beard grows in 1 second. Oh, if you can find a copy of this is great stuff. Especially if you've spent a fair amount of time reading journal articles. What do we got here? Advanced logo, discrete structures course, more discrete structures books. Over there I've got design of the Unix operating system, which is one of the very first books that documented how the whole Unix operating system worked from the ground up. Gödel, Escher, and Bach, a eternal golden braid. More discrete structures. I got books on logo and prologue programming. So I got a whole bunch of books here. This is kind of books that I like, were kind of formative for me as far as reading them and going, wow, this is eye-opening. So that's what I got going on back there. And then what you can't see down below, that I very carefully edited out, is my workbench with my current projects that I'm working on. And by projects, I mean tinkering around with old computers. Oh, let's see. This is, if I can hold this up correctly. So this is an old compact Mac. This is a Mac SE30. This is the Mac I wanted to have when I was in college. I couldn't afford it. I can only afford a Mac Plus. A Mac Plus, I think, was about $1,500. it looked like this, right? It was the same form factor, same 9-inch black and white screen, same floppy disk drive port on the front. $1,500, I think it came with a megabyte of memory, 1 megabyte of memory. And you know, no hard drive, so I was just popping floppies in and out. Once I was able to afford a second floppy drive, which was I think maybe $400 or $500 at the time, oh, it just opened up a whole new world, because now I didn't have to swap floppies nearly as much. And then when I was finally able to afford a hard drive, I purchased a 20 megabyte hard drive. I hooked that up. Again, mind-blowing. Like now I could store tons of data. 20 megabytes. You know, it's the equivalent of about 30 floppy disks at the time. And that's, you can't see it back there, but that right there, right at the very edge, is basically one of those old hard drives that I had back in college. Yeah, it was about this big. This was the SE30, which was the model that came out right when I started going to college. And I couldn't afford it because the SE30 retailed at about $4,500 when it was new. $4,500 for one of these, which in today's dollars is almost $9,000. You can imagine spending $9,000 on a personal computer. But this was state of the art. Had a 68030 processor instead of the 68000 that the Mac Plus had. At the time, it was expandable up to 32 megabytes of memory, which was like the maximum that was being produced at the time. It actually supports up to 128. Because, but since then, people produce 128 megabyte or 64, what am I trying to say? 32 megabyte memory cards. So you can put in 8 of them and get 128 megabytes of memory. But those were just simply unobtainable back in the 90s. So 32 was the maximum it could support because that was what was manufactured at the time. So right now, my goal is to expand this from the 1 megabyte it came with up to 64. And so I've gone ahead and purchased the 64 megabyte SIM cards, the memory chips, just like pretty much like the ones that go into your modern PC, except they're a little bit smaller. But the problem I'm having with it is the memory slots that the SIM cards go into, which again look almost identical to the ones inside your PC, are manufactured to 1980s, 1990s specifications, in which the SIM card circuit boards, here's one of the old 1 megabyte ones, right? They look a lot like, you know, your current ones. They're just a little bit smaller. And so each one of these boards is 0.05 inches thick, more or less. Well, 0.05 inches thick. And so the slots that they go into hold cards that are 0.05 inches thick. The problem is that those slots were manufactured using inches as their primary dimension. These days, the cards are manufactured not using imperial units, but using metric units. So the closest you can get now is a card that is 1.2 millimeters thick. That's a little bit thinner than the cards that were manufactured back in the 80s. A little bit thinner, which means that when they go into the memory slots, they're a little bit loose, just a tiny bit. Most of the time it works, but if they're just loose enough, the contacts don't make good contact and the memory doesn't work. That's the problem I'm having, was that I bought modern memory chips to go into this old Mac and they don't quite fit. Well, that's a problem. So I'm talking with the manufacturer about what can I do, and he actually suggests maybe putting some cardboard shims back behind it to just put a little more pressure on the socket, or really using rubber bands to kind of pull them forward a little bit in their sockets. The alternative would be to go on eBay and purchase some of these from back in the 80s, which may be what I have to resort to get this to work. But that's the problem I have right now, is that modern components don't necessarily fit these old computers. So you either have to buy old components, or you have to jury rig stuff to work. Oh, let me see if I can pull out this main board. So I just got to unplug some things. Unplug that. So here's the main board of the computer. Here's the 8 memory slots. I've got 1 megabyte of the original memory in there, and then I've got 64 megabytes of this new modern memory. But look, I don't know. See, these cards here are in nice and tight, and these here, they wiggle just a little bit, right? And this is causing them not to make enough contact so that they work. So when you start it up, it gives you a memory error immediately. Same problem with this, right? I updated the ROMs, the read-only memories in this computer, and this board also is manufactured to metric dimensions. And so I've got a bent paperclip here applying force to the back of the board to make it make contact. I might have to do something similar to these, somehow to push them all forward. Anyway, so here's the main processor right here, battery backup, and then all sorts of like logic chips to run the connectors on the back. What do we got here? We've got keyboard and mouse connectors. They look different than what we use now because the keyboard and mouse were different back then. We've got a floppy disk drive connector, a hard drive connector, and then the serial and the modem and printer ports, and then finally the speaker headphone port on the back. So that's the logic board for this computer. Remember, this was $9,000 worth of computer right here in my hands. I purchased this computer for 50 bucks. Someone just getting rid of it. I don't need this anymore. Oh, the other problem you have with these old computers, while we're on this topic, is you probably recognize some of these as being like integrated circuit chips. You've also got these other like silver things here. These are called capacitors. And these are used to filter out ripples and undulations in the current passing through, the electricity passing through these things. When you have signals that are switching back and forth, going from 1 to 0, 0 to 1 quickly, then it can actually introduce bit errors in other signals on the board. And so these capacitors can be used to kind of filter those out, just eliminate those. The problem with the capacitors that were manufactured back in the 90s and 80s is, and this is the problem with all capacitors, essentially, is that eventually they dry out. Or, more likely with these older ones here, is the goop inside of them, called the electrolyte, leaks out. And that's what happened to this board, is all these capacitors started leaking, and they leaked out their electrolyte liquid. And it's corrosive stuff. I mean, it's not super corrosive. It's like, it takes years and years, but eventually, if the stuff leaks out, it'll eat away at the traces, and it'll eat away at the legs of the nearby chips. I happened to get this before that was too bad. And I replaced all these capacitors with new ones, brand new ones, so this is good for another 30 or so years. Eventually they'll leak too, but hopefully be able to replace them sooner. And I got to it before the corrosion was super bad, so I was able to clean this all up, replace all the capacitors, and the computer just worked. It was great. It didn't work before, now it works. So replacing all the capacitors is what you do on computers that are this old, 30, 40 years old. Pretty easy to do with modern soldering equipment. It only costs a few bucks also. So that's the first thing I did with this. First thing I did with the other computers I had back here, replace all the capacitors. And then also in these old computers, this is probably the last thing I'll do here, also in these old computers, these run on CRTs, cathode ray tubes, old television kind of things. And it's getting kind of heavy here, but basically this is a big glass tube, and I don't know if you can see, right? But right there are a series of magnetic coils, and then back here is where the electron gun is. And so this circuit board back here generates the electrons. Those shoot down the neck of the tube and then get deflected by the magnets. And then the deflection then paints the picture you see on the screen here. Right? So the electrons come out the electron gun, they go through the series of magnets. The magnets then deflect them up and down or left and right, and they can steer that electron beam around on the CRT, the cathode ray tube on the front. Well, you need a lot of electricity to do that. Or you know, to deflect an electron beam, you need a high amount of voltage to do that. And so there's this part here, right here, called the flyback transformer. And that's what takes the relatively low voltage that the whole computer runs on and turns it into, I think, about 12,000 volts of electricity to run those electromagnets. Not a whole lot of current, but a lot of voltage. And if I were to touch that while the computer is on, I would probably find myself a moment later on the other side of the room, passed out with a concussion. Supposedly that's why it's called a flyback transformer, because you touch it and you fly backwards. And so working on these old computers when they're open and on can be dangerous. So you have to take a lot of precautions to discharge the tube, discharge all the capacitors in there to make sure you're not going to get shocked by it, which is why I'm trying to hold it very gingerly, because I'm not sure if it's been discharged yet. It should be. So if you ever find an old television set or old computer like this, you know, taking it apart is fun, but just be aware that there's high voltages inside. Even years later, there can still be high voltages inside. And you don't want to just go messing around in there and touching stuff without knowing what you're doing. So that's what my current project is. Get that thing up and running, and then I'll have my dream computer from the 1990s. And then back here, I've got some other old computers. I have an old Apple II GS, which is, again, the dream computer I wanted back when I was in high school. Couldn't afford it, so instead I had an Apple II, Apple IIe. I have one of those in the closet. Not my original one, but one just like it. I'm working on restoring that as well. And then, again, that Model 102, I got that working over the summer. That wasn't working prior to it. I replaced a couple of parts in it. Now it works great. Capacitors, a couple of RAM chips. So I don't have batteries in it right now, otherwise I would show it to you. But it's pretty simple. It's got a word processor, a spreadsheet, a simple little database, and then you can get modern like plug-in cartridges that can load programs in without having to use like a cassette deck, which you used to have to use to load computer programs into it. Now you can just basically use SD cards, load them right in, right? Old meets new. It's great, great stuff. Okay, so I think that's about it for today. There was 20 minutes of show and tell. Hope you enjoyed that a little bit. I can show you more of that stuff later on. But someone asked a couple weeks ago, what's all that stuff back there? Any questions? Oh, someone asked, are those PS2 ports? No, those are not PS2 ports. They look very similar to PS2 ports, but they aren't. They are called ADB ports, Apple Desktop Bus. So at the time when, let's see, I think ADB ports came out first. Because prior to that, the keyboard on a PC was just a 9-pin, largish connector that you used on the back. It wasn't until maybe the early 90s when they got the round connectors we use now, the PS2 connectors. And the thing about a PS2 connector is you can only hook up one device to it. You can hook up either a keyboard or a mouse. With the Mac and the Apple, you had one connector, but you could connect multiple devices to it. So the idea was, kind of like USB, the way keyboard and mouse is now, is you can connect the keyboard to the back of the computer and then the mouse connects to the keyboard. That was revolutionary at the time. You could daisy chain the devices. And the idea was you could have all sorts of input devices. I have near an ADB trackball. This is the predecessor to the current trackpad, right? You just roll the ball around to move it left or right or up or down. You got your mouse buttons here. But it has ADB ports on it, right here and right here. So you could, if you wanted a variety of input methods, you could have your keyboard hooked into the computer, and then this hooked into the keyboard, and then your mouse hooked into this. Or something else, like a keypad. If you wanted a 10-key keypad separate, you could hook that in as well. So it was called the Apple Desktop Bus because you could connect multiple devices to it. Again, this was all before USB, PS2, and things like that. So those things didn't exist yet. Here's an example of what one of those keyboards might have looked like. So here's the keyboard. Again, ADB port on this side and on this side. Interestingly, ADB was the keyboard connection for the Mac and the Apple, but it also went with Steve Jobs to Next. So Next licensed the ADB technology from Apple and used that for connecting their keyboards and mice to their computer. So the Next computer was using the Apple desktop technology, desktop bus technology to connect up their Apple's mice and keyboards. And then of course, Steve Jobs came back from Next, brought over with it all the operating systems and technology with it, and that then became OS X, which we still use today. When I was in college, I did have a Next computer. It wasn't mine. It was the place where I worked on campus. They had a Next computer, but that was what I used as my personal computer on my desktop in the computer center where I worked was a Next. And then when like Apple came out with their OS X, I went, looks just like Next, because it is. All right, 25 minutes of show and tell. I think we're done now. More later. Any other questions? No? We're good? All right then. Well, have a good day. I'll see some of you on Wednesday, where we'll go over more of these graph algorithms. And then, yeah, so we'll learn about shortest path and spanning tree on Wednesday. And then I think we'll continue a bit more with graphs, I think, on next Monday. I think. We might have some more stuff to do.
All right. Thanks,
Okay.
Professor.
Yep. Have a good day, everyone.
Take care.
Bye-bye. All right, I got a few YouTubers left. I hope you enjoyed that. Tuesday and Thursday will be C programming. We're continuing on with our programming the password cracking programs. So that'll be fun. But I hope you got something out of today. If anything, you got a tour of old 1990s computer technology. I guess middle-aged people like myself, some of them buy sports cars, some of them get into extreme sports, and then some of them buy computers from their youth, fix them up. Okie doke. Well, it's been great having you. Looks like we maxed out at about 9 or 10 people here, so that's great. Hope you all have a good day, and I'll see you next time. Bye-bye.